Hi class, welcome to today's lecture, lesson 21. So today we will talk about multiple surface and belt. So first, we will see the structure of the wedges. So by definition, it's a simple machine where small force P, okay, is used to lift large weight W. Okay, that's the definition of the wedge. So we will solve all the forces in the wedge later. And then by how? Okay, here is the steps. Definitely first, as we always did in this class, let's draw the free body diagram of the wedge first. Okay. If the motion no, the friction no too, and the friction force are just opposite to direction of motion, and the friction acts on or contacting surface. Okay, and normal face are still perpendicular. Okay, so here is the force F1, N1, our pushing force, friction F2, and N2. And then let's draw the free body diagram of the top block. So at the contacting surface, the force at the contacting surface is equal but opposite. Okay, here are the weight N3, F3, N2, F2, and apply equation of the equilibrium. Okay, so we draw free body diagram of the wedge first. Okay, but we start analysis of the top block first. Okay, because we have less analysis. Another structure is a belt. Okay, so let's see, you have T2, T1, and here is the beta. Here is the relative motion, and the beta is in radius, and if beta slip, T2 larger than T1 plus friction. T2 is definitely larger than T1. Okay, so T2 is kind of the strong force, larger than T1, so the belt is moving in the direction of T2. Another equation, T2 is just equal to T1 times A mu beta. Mu is the coefficient of friction. Beta is the contact surface, which is expressed in radius. Okay. So let's see an example. So we have the wedge. Okay. So 3000 lab applied to the wedge B, coefficient of the static friction between A and C, and B and D. The mu is 0.3, mu is 0.3. Between A and B, the mu is 0.4. Assume the wedge has a durable width. Okay, determine smallest force P needed to lift the 3000 lab load. Okay. So let's get started by drawing the free body diagram. So for the bottom one, we have NC. We have friction C equals to 0.3 times by NC. We have the push force P. We have N. Okay. Here F equals 0.4 N. And also we have the N here. We have F equals to 0.4 times by N. We have 3000 lab here. We have ND, and also we have the FD equals to 0.3 times by ND. This is B, this is A. Okay, let's get started by analysis. The top one first. So here is a B. Let's use the equation of equilibrium. Sum of fx equals to 0, which is n times sine 15 plus f times cosine 15. So we get a relationship between n and nd here. Another equation, sum of fy equal to 0. We have n times cosine 15 minus f sine 15 minus fd minus 3000 lab equal to 0. Okay, here's the equation 2. Here's the equation 1. From 1, okay, we got 0. Okay, so far we solved the nd and n. And to wedge A, okay, we have force P and C. Okay, that's pretty much for this question. So what about this one? A force P is applied to move the wedge A to the right. Okay, the spring is compressed distance So we know the mu s, we know the distance of the spring. We want to find the p. Okay, and similar, let's do the friction. Let's draw the free body diagram first. You have the p here. You have NA. FA equals to 0.35 times NA. We have the NB. We have FB. Okay, so first we solve the F spring. Sum of Fy equals to 0. Sum of Fy equals to 0. And MB equals to 2.625. FB is 0.5 times by MB, which is equals to 0.919. Sum of X equals 0. 0.919 minus NC equals 0, and NC equals to 0.919 kilonewton. Okay. And wedge A That's pretty much for today's lecture. And here is a final answer, so please check your answer and finish your homework.